Alright, welcome back. Today we're going over sliding filament theory. Let's first define what theory is in science. So the term theory means we actually don't know how something works. We just have a very educated explanation based on a lot of research and evidence. Let me give you a few examples here. So evolution. Evolution, as we learned in school, has to do with natural selection. We don't actually know for sure how evolution happens. We just have a very good idea that's natural selection based on evidence and research. Another thing is earthquakes. You've probably heard of tectonic plates before. And they're what cause earthquakes. As well, we don't know for sure, but we have a really good idea that's how it is, based on research and evidence we've collected over the years. Sliding filament theory is the exact same thing. We don't know how it actually works. We do not actually know how muscles contract on the microscopic level here, but we have a good idea based on research and evidence. So sliding filament theory sounds like a really tough, big name and sounds complicated. It really isn't. I promise you, it really isn't. So let's start. So sliding filament theory states that actin and myosin, which are basically the thick and thin filaments, don't shorten. Just the length of the sarcomere shortens, or Z line to Z line. So that may sound a little confusing. So let's go over this graph I made here. This graph should look familiar if you watched my videos, like my 3 videos ago. Yeah. If you have not watched that video, I highly suggest you do, because I'm going to go over stuff like myosin, actin, titin, I band, M line, Z line, and A band. So I highly suggest you watch that video before watching this one, so things will actually make some sense. So in my previous videos, we've gone over that during a contraction, myosin heads basically grab on to actin, so these little heads, and they pull on actin. What's happening is the length of actin does not shorten, nor does the length of myosin shorten. What's actually shortening is the length of the sarcomere, or Z line to Z line. So it's this section right here. So the distance between Z line to Z line, that's what's shortening. So you must be wondering, well, how is that possible? How can it shorten? How can it actually shorten without shortening the actual filaments? Well, what's actually happening, and this is how the sliding filament theory, the name, comes in, is that what's happening is the myosin filament and the actin filament, they're sliding with each other. So when they pull, actin slides this way, and actin slides in that way. And it's causing essentially sliding to happen. The distance where actin is, there's no actin, is getting shortened, or the H zone. Let me give it to other terms. You have two people here. They're pulling sleds. And what's going to happen here is, let's say this guy on the left here is going to walk this way, and the guy over here is going to walk this way. The length of the sled will not change, nor will the actual human change. What's actually changing, the only thing that's changing, is the distance between the two people. If they walk towards each other, the distance, the space between them, is going to get shortened. Sounds familiar? Well, this is literally like the H zone, right? H zone. The distance between the actin filaments, pretend the actin filaments are the people. The distance will shorten. This distance will shorten when they contract. So the H zone will be probably like this length. It will be shortened. The other thing that will be shortened is the I band. The I band is the length of the thin filament when there's no overlap with myosin. So with sliding filament theory, during a contraction, what it states is that myosin and actin are going to be overlapping even more. If this goes in this way and this goes in this way, there's more overlap going to be happening. If there's more overlap happening and they're basically the same size during contractions, the I band is going to shorten, because that's the space where there's no overlap. So let's just say in a non-contracting muscle, we have, let's say, 50% overlap and 50% no overlap. So 50% of the 50% of the sarcomere are overlapping. So actin and myosin, 50% are overlapping, and the other 50% are not. Now during the contraction, let's just say there is now 75% overlap and 25% no overlap. Remember I told you the I-band is the non-overlapping region where there's no overlap between actin and myosin? This is technically the I-band. What color did I did it orange. Let's do orange here. So this is the I-band. I hope that makes a little more sense. So what it's basically saying in sliding filament theory is that actin is sliding past myosin. So the only bands that are shortening are the H zone, which we've gone over. That's the distance in the middle, the length of the myosin filament only when there's no actin. The I band, which I just explained above, it's the length of the actin filament by itself, or the basically the no overlap region when there's no overlap happening between actin and myosin. And the Z line, which is the length of the sarcomere, those are the only things that are shortening. So let's just go over the Z line again. The Z line over here, this space is becoming shorter. It's contracting. That's what's happening. Everything's getting squished together. Just think about it like that. Everything's getting squished together. The length of the actin filament's not changing, nor is the myosin. They're just getting squished together. The space, look how much space there is here. This is basically what the H zone is the amount of space they can move in. Then it's going to cause crushing and nothing. Then it's going to be a problem. But look at how much space myosin has to contract and go in before being crushed. That's what the H zone basically is. Hopefully this made sense. And the only big takeaway is sliding filament theory is that actin and myosin actually don't shorten. It's not you're not cutting off sections of actin and myosin to contract. No. That's not what's happening. It's just getting shorter because we're just compressing it. And what basically happens is they're sliding past each other. That's what the sliding filament theory states. If you found this useful, please like and subscribe. And until tomorrow, later.